Hi. So my name is Yochai, and I'll first of all thank you. It's a great privilege to be talking to such an audience. And first of all, I made a little animation. I have many people here are Jay's scientific sons or grandsons, or we had his fathers, and most of you are his scientific brothers. And I think I thought I was the only one who I was in a very peculiar situation, because I spent quite some time in Eran Sharon's lab, and then quite some time in Eran Buchmander's lab. So Jay is my grandfather from both my mother and my father, which is probably illegal in most states. But over lunch I realized that Jay is his father and grandfather, which is probably worse. So I'm not.
Stepson through the coast, so it's not a.
Okay. It's like Woody Allen kind of, yeah. But seriously, this was not planned. I want to say that I arrived in Eran's lab when I was in undergrad, and there was this Eran J, bubble of the physics community in Givat Ram, and what I still remember, like almost probably 10 years ago, is mainly the atmosphere. The way it was simply a great place to be. There's the coffee table. I don't know how many of you know the coffee table, but the coffee table is where everything happens. Jay comes, makes black coffee. Eran makes black coffee and adds some instant coffee on top, just to be on the safe side, with the caffeine, and they just contemplate and talk about science and not science. And I really remember at the time Jay was the head of the institute, so he had like tons of stuff to do, and Eran was not tenured, so he actually had to work, like not like you. And they still took their time to just sit and talk about stuff, and I not to forget what this is all about. It's about thinking, asking nice questions and giving nice answers, and yeah, I think that's something that I try to retain. So, by the way, then I went to perfect my abilities in drinking coffee and talking about non-interesting stuff. So I went to Paris to do my master's, which is arguably the capital of. Never mind. Okay, so let's friction. I'm going to talk about friction. So let's imagine you have two bodies which are sliding. They can have different properties, like shear moduli or whatever, elastic moduli. And in each body, you have the equations of elasticity, because far away from the fault, everything is elastic. And then in the middle, you have some friction law, and this is basically the problem of friction, right? That's everything. This is very complicated. So there have been many debates about what should be the proper description of the friction law. We've had some talks today. But I'm not going to talk about this. I'm going to talk about the other part. I'm going to talk about the elastic parts, which make things pretty complicated. So even after you understand what does a single thing do, the elastic coupling between different points of the interface makes things very, very difficult. So at least for linear, flat interfaces, what one can do is to reduce these equations to interfacial dynamics. You can integrate out analytically everything that happens in the bulk and reduce everything to an equation on the interface. And it looks like this: the sigma y I, and I is x or y, so it's either the normal stress or the shear stress, is given by some convolution of some Green's function, gi, with respect a convolution of this with the difference between the discontinuity in the displacement field along the interface. So it's the difference between the velocity field, the displacement fields of 1 and 2. So first of all, we give this thing a name. We call it epsilon. This is the discontinuity of the displacement field. And then we do what we should do in linear problems, and we go to Fourier space. So in Fourier space, it looks like this. Again, sigma yi in Fourier space is k times a Green's function, which is the Fourier transform, and it simply multiplies the Fourier transform of the displacement for the discontinuity. And it turns out that it's more convenient to work with, not with omega and k, but with c and k. C is the phase velocity, omega over k. Okay, so this equation is going to be, this function g is going to be the main player in this talk. The first one to calculate these functions was Wirtmann. Generally, for an infinite 2D system, so you have one material below, another material on top. I didn't write the equations here because they're horrible, but I can. The graphs are okay. So this is he uses it. So yeah. So this is the transfer functions gx and gy. So gx is the response of the shear stress, and gy is the response of the normal stress as a function of the velocity. And they have some functional form. The important thing is that they diverge at the shear wave speed, or at, to be more exact, at sonic velocities. I don't want to be too specific here because it's delicate, but they diverge at sonic velocities. Just to, because he's here, so Michael also calculated the transfer functions for finite blocks. I can give you a taste. This is how it looks like. It goes at least a few meters to the right, and all these are abbreviations. So if you're interested, it's in his paper. I'm sure you're all interested. I'm kidding. Yeah, no, just I'm advertising as it is. Just, but there is some very useful and very nice simplification that happens if the two materials are identical. So this is from Wirtmann. And I quote, if the two half spaces have identical properties, only shear stress is produced. On the other hand, if the fault separates two half spaces with different properties, two traction stresses are produced. You have the shear stress and the normal stress. So if you have the same material, gy, do we have gy? Gy is this thing, the coupling of the normal force simply goes to zero. And this is what is called the bimaterial effect. In some, I want to put it in quotes because it's not only a bimaterial effect, but the coupling of interfacial shear motion and normal stress. It only happens in a bimaterial fault, and it's very easy to see why. It's a simple symmetry argument that I want to follow. Let's say you have this system, you have the tangential slip, you have the normal stress. Now you take the system and you flip it on its head. Okay? If you have a symmetry, if it's the same thing, okay? So the slip discontinuity changes sign. The normal stress is it's a linear problem, so it has to change sign too. But you know, if it's compressed and you flip it, it's still compressed. So it must be zero. It can't be non-zero and flip signs, right? So this is basically the argument. Okay, if you have the same material, you can't have coupling of shear motion to normal stress. With different materials, you can have it. And this is the interim summary. It diverges the bimaterial effect, that is the coupling of shear motion to normal stress, diverges at sonic velocities, is elastodynamic, and it vanishes if you have symmetry. And we know this for 50 years, or probably more. And then we had Ilyas experiment. And I remind you, you have two blocks, you slide, you have this really magnificent fit of LEFM fields, and you have this little thingy. So this is the area of contact as a function of space. This whole thing moves to the right. It's a rupture front with different velocities. There are three measurements. And you can see that at small velocities, the orange and the blue, you have some decay. But at very high velocities, you have this bump. And this bump is interesting. And even in the paper, the original paper that they published, it says the non-monotonic behavior of A suggests interesting dynamics as C goes to CR, the Rayleigh wave speed. And Ilya has been for years been telling us that this is the bimaterial effect, which we, of course, as theoreticians, we sneered and say, well, you need two materials to have a bimaterial effect because, you know, this is what Wirtmann says, but let's see. Does it diverge under sonic velocities? Well, it only happens when you are at very high speeds. So I don't know about the divergence, but it's certainly only observed at high speeds. What? Okay. Is this an elastodynamic effect? Because one might say, this has nothing to do with elasticity. Maybe you know, when the area goes down, you know that if you follow this line way, way, way to the left, it's going to go up again, right? Because you have frictional aging. Maybe this is some kind of frictional aging that happens at high velocities. So for this, we can ask. So the contact area is the normal stress times some quality of the interface, like what Elsa talked about, this thing that measures how much the interface is aged, and this might be dynamics of psi rather than the normal stress. So you can go to this paper by Oded, Shmuel, and Jay from 2010, and you can compare the time scales. You can see the growth of the area, and you can see that it grows logarithmically, and just like Rob talked about, at low time scale, at small, very short times, this logarithmic growth is cut off. And you see this happens at around a millisecond, and you can estimate the time here. So this is space, it's about 1 millimeter. The velocity is about 1 kilometer per second, so you can estimate the time, it's about 10 to the minus 6 seconds. So this is like 2 or 3 orders of magnitude too quick, so we have to conclude it can't be dynamics of psi. And then you can ask whether it vanishes under symmetry. So you take this block, and this is the measurement, and then Ilyas was kind enough to replace the bottom block with the same block, and this is the measurements that he got, and then it was pretty convincing. You know, it walks like a duck, and it talks like a duck, and it's probably this. So let's go back to the original argument. We need to have symmetry. So usually what people talk about is that they take different materials, but if you take different shapes, well, this is not symmetric anymore, right? So in general, it shouldn't be called the bimaterial effect, it should be a symmetry effect. So GY, the coupling of shear motion to normal stress, you only need asymmetry. And I also made like a thing that will help you to remember. Now you all remember that all you need is asymmetry. And also in the same single there was baby or a rich man, which doesn't apply here. So now let's do theory, because this was pretty convincing, but the nice thing about this system is that we can actually almost quantitatively reproduce everything. So this is the plan. First, we're going to calculate the quasi-static response for each F system. So we have the top block and the bottom block, and at least in the quasi-static limit, we can calculate how they respond to stresses on the interface. Then we're going to, hopefully, we need to cross your fingers, extract effective elastic constants. We hope that under this reduction of this quasi-static response will be effectively like a 2D real material. We hope. And then we're going to use the effective constants that we extracted from here in Weertsman theory, which we need to cross like 2 fingers because the Weertsman theory is applied at sonic velocities, and this calculation is quasi-static. Okay, so this is incompatible, but since I'm telling you about it, you can guess it works. And we're going to compare to experiments, which is really a long shot. But it all works. So I'm telling you then. So how do we calculate the response of the system? The top half is very easy to model. We just model it as a 2D block, like an infinite half-plane 2D. And the response function is easy to obtain. Just read it from, I think, one of Jim Rice's papers, like everything. And this is the stress at the interface. This is the displacement at the interface. And we have this matrix. This is some matrix. And you see it has complex numbers because we're in Fourier space. So, and the only k dependence here is in this prefactor. So this k here is the wavelength, or the wave number. Okay? So this is easy. Now, what do we do about the bottom block? So the bottom block is not 2D. It has no symmetry. It's a 3D thing, or a half space, but it is only loaded on a finite strip. So we just integrate the response function of a elastic half plane, which is, you can also read the response function in Landau-Lifshitz, and you just integrate it over the width of the part where you do the loading. You don't want to do the integrals. They are really horrendous. As you can see, when you try to calculate analytically here, it becomes very ugly. But they are tractable analytically. I mean, yeah, we have a closed form expression for them, but it's so horrendous that we had to pick up a name. So we call them B, C, and D. They are just three functions that we have like integrals of Bessel's functions. They're ugly, but they are functions that we can calculate. So these are the two components. This is the top block, the thin one. It's simply a 2D half space, and this is the 3D half space. And now we hope that we can extract some effective elastic constants. But you see that you have a problem, because this matrix is nice and symmetric. I mean, this is the same as this is the same as this, but with a conjugate. And here we have this symmetry, but this is not the same as this. So you can't map this to this. It doesn't have the same symmetry. Yes?
Very nice question. So why doesn't the first one have W in it? That is the width thickness of the thing. Why?
Because it's a 2D, in 2D plane stress approximation, the width just goes out.
I'm hearing words, but the thing is this thick. That's the point, no?
No, if you assume zero stress on both sides, the width just goes out.
All right, whatever.
And you can ask Landau or Lifshitz about it. Or read Rand's lecture notes, by the way. But luckily, if you plot C as a function of the wavelength, it simply is not very large. When the wavelength, so we have a dimensionless parameter here, it's the wavelength times the width, and it's when the wavelength is much shorter than the width, then this thing, or not even much. So 6 is 2 pi. 6 is when the wavelength is equal to the width. Okay, so this is not, so when the wavelength is roughly of the order of the width, this C thing is simply negligible, and then we can just map exactly, or approximately, the system, and we can have an effective, so this is nice, we have an effective effective shear modulus, which depends on K. And we have an explicit expression for it, and this is how it goes. And you see that quite intuitively, the effective shear modulus of the 3D system is larger than the shear modulus of the 2D system. Because when you have a 3D thing, this is not very robust. I should use VGA. So when you pull on a 3D thing, you pull more stuff with you. Okay, so you need to invest more force and more energy. So the 3D block is effectively, in the quasi-static limit, more stiff than the 2D block. And then you can just take this number, and you need to apply it to Weizmann theory. How much time do I have?
You have actually 15 minutes.
15?
Well, 10.
Wow.
You started late.
No.
10.
Okay.
10.
No, I need to find stuff to talk about. It was all very easy.
No, it's
Nice.
good, it's good, it's good.
Okay.
Just stick to time.
So now we apply Weizmann theory. So we have
I made the mistake, 7.
okay, thank you. We need to apply Weizmann theory. There are two materials effectively, one with mu and one with mu effective. But this depends on K, and this is a bit flimsy. And we want to, I remind you, explain this. So this is the contact area as a function of the velocity, and we want to explain this bump. So if you go through the algebra, you see that this is the result. The drop in the normal force, which is proportional to the drop in the contact area, is proportional to G, which is a function of K, to V, which is the particle velocity at sliding, and inversely proportional to C, the phase velocity. Okay? So we have all these, and all these things, K, V, C, G, they all change between the fronts. So it's a bit, and everything is, of course, approximate. But let's see. V over C. So this is V. With the same color code, you have 4 fronts here and 4 fronts here. This is V. It's calculated using some model for the crack, which is okay. And you see that V changes a lot between the very fast one and the very slow one. This is a factor of 10 almost. Okay, so this is a very important factor. Let's see about G. So G is also, it's a bit delicate because you need to pick a K. So we pick here 3 Ks just for to have some concrete values, and you plot G as a function of c for these three specific k's. I know it's a bit complicated and it's late, but bear with me. So they all go to infinity when you approach the sound speed, but we do not approach the sound speed, right? We approach the Rayleigh wave speed, which is below. So we are around here, and you see that the variation in the propagation velocity in c is pretty minute. We go from 0.9 to 0.99, so it's like 10% variation, so it's something about this range. So at this range of variation, we simply take g to be a constant, a k-dependent constant, but some constant. Okay, and then we end up with delta yy is g times v over c, and c is a constant, it's just the Rayleigh wave speed, and g is a constant, so it should only be proportional to v in a very simplified theory, and this is what they measure. Okay, so this is the drop in the contact area, and by they I mean the royal they, it's Ilyas.
Divine they.
The divine they, yes. And this is what they measure, and you can ask what the slope is, and the slope corresponds to kw is 3.3, which incidentally the value that we guessed to begin with. No, I'm kidding, but kw equals 3.3 means that the wavelength is half roughly the width, which is it's a reasonable number. It's not far-fetched. There is some deviation here, so our prediction says that this line should go through 0, and their data does not go through 0, but this is because, yes?
Maybe I'm stupid, but can you tell me why sigma yy is proportional to
To
the area?
the?
Area, the A?
Well, that's Bowden and Tabor. That's like, that's the basic,
Louder than
yes.
table.
I mean, that's the basic model of, yes. Yeah, so we measure, we predict basically, this is an elastodynamic calculation, we say nothing about friction, but on top of that, you remember, there's also a decrease of contact area because there's rupture. So this does not come into account when we think that this should, so basically at very low, this should at least explain partially this offset. And of course, if you do the same thing with symmetric, with the thin on thin samples, then, well, this effect vanishes. So this is cute. I think it's nice because you take a system and you can analytically solve something, but you can say, well, we don't get many, thin on thick blocks in nature. What about this, for example? So this is a subduction zone cartoon. You take one tectonic plate that goes beneath the second one. It's also an asymmetric system. And here also you should expect a priori to have coupling between shear and normal traction. And by the way, I forgot the most important thing, sorry. This effect is quantitatively important. If you remember Adar's talk, where is Adar? Don't you see? This effect is quantitatively important in selecting rupture mode and rupture direction, and it makes the dynamics of rupture rich. So the fact that you have a breaking of symmetry, that gy is non-zero, is quantitatively important. Even here you can see that the reduction of the normal stress on top of what friction does, so this is the elastic reduction, this is the frictional reduction, is like an extra 30% of weakening exactly when friction is happening. So this is a quantitatively important effect. So you want to ask maybe it's important in subduction zones. So this is, it calls to be done. We didn't do it because it's a complicated calculation and I was finishing my time, but we can do this. This is a relatively easy calculation, and we can, if you squint your eyes a lot, you might think that this is related. And here, for example, here, for example, we can do, so let's forget about this and work only with this. You can ask about stability of frictional sliding. Okay, so just for the sake of demonstration, we did also a more general analysis, but just for demonstration, assume that the friction force is simply a function of the velocity, and assume that it is an increasing function of the velocity. So the FdV is greater than 0. This means it's a velocity strengthening interface, it's stable. It shouldn't, intrinsically, the frictional part of the motion should not be unstable, okay? Now, if you go through the math and you do the algebra, this is a non-dimensional parameter that characterizes the importance of the elastodynamics. This is mu over c. It's what is called the radiation damping. And this is the frictional strengthening. So they compete. And you see that for some, so what I plot here is the, ignore the dashed line, just the solid lines. Okay? This is the imaginary part of the phase velocity. That is the growth rate of a perturbation. So you see that for some values of gamma, there's an intermediate value for some values of gamma, there's an intermediate value of k, which is unstable. So you take a system which is frictionally unstable, you put it in an asymmetric configuration, and simply this elastic coupling of shear to normal stress can give you destabilization, which is, and all these unstable modes travel roughly at the Rayleigh wave speed. So this is the real part. It's the phase velocity, and it's roughly the Rayleigh wave speed. So it might be, we believe it is, quantitatively important in understanding asymmetric faults, which is, as Hadar said, the generic case. Conclusions. So geometric asymmetry can induce coupling between shear motion and normal stress. There is one particular, or two particular cases where we can solve this analytically, for the thick and thin geometry and for this geometry, which they have quantitative implications. And just to finish, this is a very recent paper from Nature about experimental evidence that thrust earthquakes ruptures might open faults. And I quote, "This is due to the break-in symmetry of the fault geometry in interaction with the free surface. The torquing mechanism is geometrical in nature and allows for natural reduction in elastic compressive normal stress." Basically, they're saying what we say also, but without citing us, which is also okay. How much time do I have? Do I have 1 more minute? 1 minute. I just want to say, we talked about Wirtman, and this conference is called the first 6 years of Jay's Feinberg's career. So this is a page from Johannes Wirtman's last paper that I know of, 2011. He was 86 at the time. It's a single author paper. And I think, I mean, you have stuff to aspire to. And also Wirtman has an island named after him in Antarctica. So yeah, maybe someday. Thank you.